students, so welcome back. Last time we have done Arrhenius equation and collision theory. So today we'll be doing the last section, zero order reactions and first order reactions and their half-life also. So let us begin with zero order reactions. Now see, for a zero order reaction, say example A giving you products, and I'm assuming that this is a zero order reaction. Then for a zero order reaction, this is the equation. Amount of A left after some time t equal to initial amount A naught minus KT. And when you will plot this graph with AT on the y-axis and time on the x-axis, you will get a negative slope. Okay, so remember this graph. I mean, sometimes in kinetics graphs are very important. They can ask you sometimes the questions on graphs directly. Now you arrange that, rearrange that, and you will get time equals to A naught initial amount minus the remaining amount upon K. So from here T half we can say is A naught by 2K. Remember that half-life is directly proportional to the initial amount. More is the initial amount, more will be the half-life. This is very important. You got to note it down. Okay. And the examples of photochemical reactions are, zero order reactions are photochemical reactions and gaseous reactions in presence of catalyst, a solid catalyst, maybe metal, at high pressure. Remember that it is at high pressure. Now let us solve a question on that. A reaction is given, a zero order reaction, and they have given if A naught is given as 2 molar, half-life is 1 hour. They are saying find time taken to bring concentration from 0.5 to 0.25 molar. Now I want you to focus on this. 0.5 to 0.25 molar. The substance is becoming half. So they are actually asking you half-life. And I know that half-life is directly proportional to A naught, the initial amount. So I can write down that T half is proportional to A naught. Okay. Now from here I can say that T half for the first case, say this one, upon T half of the second case, this one will be equal to A naught of the first part. I mean, this is the A naught of the first part upon A naught of the second part. Second part will be initial amount. Initial amount will be 0.5. So from here I can say that T half is given as how much for the first part? 1 hour. I am supposed to calculate this T half equal to A naught here is 2 molar and A naught here is 0.5. So you will see that this will be 4 by 1. So I can say by rearranging that T half will be what is required to bring concentration from 0.5 molar to 0.25 molar will be 1 by 4 hour. And this will be equal to 15 minutes. So this is how you are going to do the question. I hope it is clear. Okay students, now we have come to the last part of this chapter, the first order reaction, and that is the most important part of this chapter. Most of the questions are asked from first order reactions only. So let us come to first order reaction. I have again taken a first order reaction. And the equation of first order reaction is log of AT. AT is the amount of substance or reactant remaining after time t equals to log of A naught. A naught is initial amount of the reactant minus of KT divided by 2.303. Now if you will plot this graph of this line with log of AT on the y-axis and time on the x-axis, you will get a negative slope, with slope being minus of K upon 2.303. This is very, very important. You got to remember that. And when you will rearrange this equation, you will get K equals to 2.303 upon T log of A naught by AT. This is a very important equation because many questions will be solved by this equation. Now come, when you will try to find the half-life by putting AT equal to A naught by 2, you will come across that half-life is 0.693 upon K. The significance of this equation is that half-life is independent of the initial amount, unlike the zero order reaction where the half-life was directly proportional to initial amount. Here half-life is independent of the initial amount. This is very important. And there is one more form of first order reaction, the exponential form. This is AT equals to A naught into e to the power of minus of KT. When you will plot the graph with T on the x-axis, AT on the y-axis, you will get this graph. This graph is never going to meet this thing. Okay, remember that. The best example of first order reactions are all radioactive reactions. All radioactive reactions are first order reactions. Okay, now let us do some questions on this. Okay, so students, now we are on to half-life of first order reaction. Let's go into the details of this first order reaction half-life. So I am taking an example. Suppose I begin with 100 particles. After one half-life, I will be left with 50 particles. Half-life means half of the substance will be remaining. After one more half-life, 25. The half of 50 is 25. After one more half-life, 12.5, the half of 25. And after one more half-life, 6.25, the half of 12.5. Now see, what I am saying is that when I complete one half-life, I have completed 50% reaction. That means 50% reaction will be completed in one half-life. But when I go from 100 to 25, the 75% reaction is over. So while the 75% reaction is over, from here to here, how many half-lives we have covered up? We have covered up 2 half-lives. So T 75%, that means time taken to complete 75% reaction will be 2 half-lives. Similarly, this is 87.5. From 100 to 12.5, if I come, I have completed 87.5% reaction. How many half-lives? 1, 2 and 3. So on completing 87.5% reaction, I have covered up 3 half-lives, or 3 half-lives are required to complete 87.5% reaction. Similarly, to complete 93.75% reaction, how many half-lives I have covered up? 1, 2, 3 and 4. So to complete 73.75% reaction, I require 4 half-lives. Now these are very, very important data, because they sometimes ask you direct questions on that. So if you are able to remember this data, your job will be very simple now while solving the question on first order reaction. In first order reactions, remember students, it's very important that you command the half-life aspect. Now see, some more data, but very crucial data. Time taken to complete 90% reaction. T 90% means time taken to complete 90% reaction will be equivalent to 3.3 half-lives. Time taken to complete 99% reaction will be equal to 6.6 half-life. Time taken to complete 99.9% reaction will be 10 half-lives. And time taken to complete 99.99% reaction is 13.2 half-life. In the previous, 12-13 years, NEET has asked some 6 or 7 questions directly, indirectly on this aspect. Though this is very crucial. One year they asked, what is the ratio of T 99% and T 90%? So from this data, see, there is one more method, the conventional method, which can take you a lot of time. But if you remember this data, see how simple your job is basically. T 99% is how much? 3.3, this is T 99%, 6.6 half-life upon T 90%, 3.3 half-life. Half-life cancels up, this will be 2. So the ratio of T 99% upon T 90% will be 2. Similarly, the ratio of T 99.9% and T 90% will be, this is 10 half-life and this is 3.3 half-life. So half-life will cancel up. 10 divided by 3.3 will be approximately 3. So this is how you are going to do these questions. Just command the half-life aspects. Your job will be very easy in terms of solving the questions of first order reaction. Now let's solve some more things. Okay. We are on to a very good position in terms of handling the questions of chemical kinetics. I just want to share a very important piece of information regarding half-life. So let's see this. And amount of reactant remaining after n half-lives will be A naught, the initial amount, upon 2 to the power of n. This is very crucial information, very crucial information. Then in general, for any order, the half-life is proportional to 1 upon A, the initial amount, to the power of n minus 1. N is the order of reaction. This is very, very important, and the significance of this equation will be seen here. So I have divided the orders like 0 order, first order and second order. So for zero order reaction, half-life is proportional to A naught, the initial amount. When you will put 0 over here, this will be A to the power of 0 minus 1, that is A to the power of minus 1. This will move up. So half-life is proportional to A naught. We have earlier seen in the zero order reaction also. So that means for a zero order reaction, half-life is proportional to A naught. More the amount, more the half-life. Remember that. And the plot of this graph will be half-life on the y-axis, A on the x-axis. It will be a straight line passing through origin. Now for first order reaction, we all know that half-life is 0.693 upon K. It is independent of initial amount. So it will be constant. Remember that for a first order reaction, half-life is constant. It is independent of the initial amount. So and the graph will be T half being constant. Okay. Now for second order reaction, T half is inversely proportional to the initial amount taken. If you plot this, T half here, 1 by A here, remember this is 1 by A, and it will be a straight line passing through origin. The crucial thing to be noted about the second order reaction is that more is the amount, less will be the half-life. It sounds bit abnormal, but this is fact. More is the amount, less will be the half-life. It is inversely proportional to the initial amount. Okay. Now let's see how to apply these formulas in solving questions. Okay. So students, let's see how to apply the concept of half-life in the questions. Okay. So the first question is for first order reaction. All these three questions are for first order reaction. They have given you half-life as 6.93 seconds. They have given you the amount of A, 10 molar. They are asking find rate of reaction when the amount of A is 10 molar. Now see that for a first order reaction, rate will be Ka to the power of 1. This is a first order reaction. Okay, now I know A, this is given to me. I need to find out K, and for a first order reaction, I know that K is equal to 0.693 upon T half. T half they have given me. So I can very well calculate this will be 0.693 upon 6.93. That will be 0.1. Okay. Now R equals to Ka. I know that. So put the values. This will be K will be 0.1 into A will be 10. This will be 1. So rate of reaction will be 1 moles per liter per second. The time is given in second, and this is molarity, so moles per liter. Okay, I hope this question is clear. Now come to the second question, again for first order reaction. Here they have given you initial amount 1 molar, final amount is given as 0.25 molar. Time taken is given as 20 seconds. They are asking you find K. Now to find K, I should know the half-life. So if you focus on this question, see that if I begin with 1 molar, after 1 half-life, it will be 0.50. After 1 more half-life, it will be 0.25 molar. Okay, so this is half-life, this is also half-life. Total time given is 20 seconds. Time required to go from 1 molar to 0.25 molar is 20 seconds. So this is how much? 2 half-lives. So 2 half-life is equal to 20. So half-life will be equal to 10. So half-life is 10. They're asking K. So what is K? K will be 0.693 upon 10, the half-life. So this will be 0.0693, and the unit will be per second. Remember that for first order reaction, the units are per second, per unit time. Now come to the last question of this category. Again a first order reaction. They have given initial amount as 80 gram, half-life is given as 5 hours. They are saying find amount of A remaining after 20 hours. So we know that amount of A reactant remaining after n half-lives is what? A naught initial amount upon 2 to the power of n. We have discussed this formula just right now, and that will be equal to A naught is given as 80, and number of half-lives in 20 hours. Half-life is 5 hours. So number of half-life in 20 hours will be number of half-life will be how much? 20 upon 5. That will be 4 half-lives. So n will be 4. So 2 to the power of 4. This will be 80 by 16 and that will be 5 gram. So after 20 hours, that means 4 half-lives, the amount of substance remaining will be 5 grams. Okay. Okay, students, come and let's solve this question. This is the first order reaction and they're saying that it is 90% complete in 40 minutes. That means they have given you T 90% equal to 40 minutes. They're asking you half-life. So you all know the relationship between T 90% and T half. You know that T 90% is equal to 3 into 3.3 into T half. So T half can be written as T 90% upon 3.3 and that will be 40 minutes upon 3.3, which will be approximately like 12 minutes. So I already told you that these relationships are very, very important in terms of half-life. Just command them, and in examination actually they are looking for something unique and most of times they are looking after half-life. So please do command the questions of half-life. Your job will be very easy in terms of examination. Now come to this question. This is a first order reaction. So they have given you two situations. When the A naught is 1 molar and the final product remaining is reactant is 0.6 molar and time taken to come from 1 molar to 0.6 molar is 10 minutes. They are saying that if we begin with 0.6 molar and we want to come to 0.36 molar, the remaining amount 0.36 molar, how much time will be required? Now see, for a given first order reaction K, the rate constant will not change because rate constant depends only on temperature and other things, but not on concentration, so K will remain same. So K for both of them will be same, that will be 2.303 upon T log of A naught. A naught here is how much? 1 molar upon 80.6 molar and K for this will be how much? 2.303 upon T log of A naught, how much? 0.6 molar upon 0.36 molar. Now since they both are equal actually, so can we equate that? Yes, we can definitely equate that. This will be 2.303 upon T is given as 10 minutes log of 1 upon 0.6 should be equal to 2.303 upon T, we have to find it out, and log of 0.6 upon 0.36. Now see student, this will be cancelled up. If we solve it, this will be gone and this will be 1 upon 0.6. So this ratio is equal to this ratio. This can be also cancelled. So we are left with T equal to 10 minutes. So T will be 10 minutes. So remember that this question, the significance of this question is that if you take the ratio, the fraction will be same. For both of them, the fraction is 1 by 0.6 and 1 by 0.6. So what I'm trying to say is that to cover or to finish the same fraction of reaction, the time required will also be same. In a first order reaction, I repeat, the time required to complete a reaction by certain fraction will be same always. How come? Let's see in the other examples. Okay. So students, I'd like to share a trick with you to solve these kind of questions in one go. Remember that same amount or same fraction of reaction will need same amount of time to be completed. I'll explain that, but first read this question. Amount of substance becomes 1/3 of its initial amount in 10 seconds. Calculate the time taken to reduce the initial amount to 1/9. So let's take the initial amount as 1. It will become 1/3 in 10 seconds. Now they are asking you how much time it will require to reduce the initial amount to 1/9. So you see 1/9 is nothing but 1 by 3 of 1 by 3. So it will be 1 by 9. So this is how much? 1/3 it has become. So 1/3 of this will again require the same amount of time. Same fraction of reaction will require same amount of time. So total time required will be 10 plus 10, that is 20 seconds. Say for example, if they ask you that the initial amount is 1 and time taken to become 1 by 5 is say 10 seconds. Time required to become 1 by 25, that is 1/5 of this one, will again be 10 seconds. This is very, very important, students, to solve certain questions. If you are looking for the same fraction or same amount of time, it will take same amount of time to complete same amount of reaction. Okay, students, just listen to me very carefully. I am just sharing a very strong trick to solve certain questions of first order reaction. See that if I begin with initial concentration of say 1 molar, after 1 half-life, say it is say 10 seconds, it will become 1 by 2. After 1 more half-life of say 10 seconds, it will become 1 by 4. After 1 more half-life, that is 10 seconds, it will become 1 by 8. So what I am trying to say that the amount of reaction or amount of time taken to complete 1/2 of this reaction every time requires same amount of time. That means 50% of reaction will take place in same time wherever you begin with. And this concept applies to not only to 50%, it applies to every percentage. Wherever you begin with, the amount of time taken to complete the same fraction or same percentage of reaction will require same time. Say for example, if I begin by 1 and time taken to complete this much fraction of reaction is suppose say 10 seconds. Again, going to 1 by 25, 1 by 5 of this one will require 10 seconds. So that's a pretty good trick to handle the questions. So we'll be solving this question with the help of this trick. This question says that initial amount of substance become 1/3 of its initial value in 10 seconds. You have to find out the time taken to reduce the initial amount to 1 by 9. So that actually means I'm beginning with 1 molar. It will become 1 by 3 in 10 seconds. And I want 1 by 9. So 1 by 9 is what? 1/3 of 1 by 3. So it will also require same time because I am going to finish up the same fraction of reaction 1 by 3 and 1 by 3. So it will also require 10 seconds. So time taken to reduce this initial amount of 1 molar to 1 by 9 will be how much? 10 plus 10, that will be 20 seconds. So 20 seconds will be required to reduce the initial amount to 1 by 9. Okay. So students, let's see one more question on first order reaction, and this question says that it is 20% complete in 10 minutes. They are saying find time taken to complete 75% of the reaction. So how you will proceed in any given order of reaction? The K value does not change for a given reaction until and unless you are changing temperature or using catalyst otherwise. Okay. So here we are not changing anything like that. So I know that K will be 2.303 upon time taken for 20% and log of initial amount, let it be say 100. So whenever they give you percentage, begin by 100, and once it is 20% complete, remaining amount will be how much? Remaining amount will be 80. Now this K should also be equal to the second part of the question, 75%. So it will be 2.303 upon T log of initial amount is 100, and once it is 75% complete, the remaining amount will be 25. So it will be 25. Now this T is actually given as how much? 10 minutes. So this part can be cancelled up. This will be gone and this will be 4. Now let's resolve this. So this will be log of 10 upon log of 8 means log of 10 upon 8 means log of 10 minus log of 8 upon 10 should be equal to how much? Log of 4. So log of 4 upon the time taken. Solve this. This is 1. Log of 8 is how much? 0.9 upon 10 should be equal to log of 4 is how much? 0.6 upon time, which they are asking. Basically this will be 0.1 upon 10 should be equal to 0.6 upon t. You solve it, 10 into 6 will be 60. So time required to complete 75% of the reaction will be 60 minutes. So catch here is that K will not change for the single reaction. It will remain same whether you are asking 20% completion of reaction or 75% completion of reaction. Okay. So students, this is a very interesting question, and they have given you a reaction. P and Q are reacting to give you products, and they have given that for P, T 75% time taken to complete 75% of reaction is double of time taken to complete 50% of reaction. For Q, the graph is given with respect to time. They are saying find rate law. To find rate law, I have to know the order of reaction with respect to P and Q. So see, now for P, in which case you have seen that 75% of reaction will require twice of half-life. That is for first order reaction. So with respect to P, it is first order reaction. And this graph, concentration on the y-axis and time on the x-axis, and we have a negative slope. With slope, you know that this is minus of K. This is a zero order graph. So with respect to Q, it is a zero order reaction. So overall rate law now will be R will be equal to K, P to the power of 1 and Q to the power of 0, because the order of reaction with respect to Q is 0. So that will be the final rate law. And overall order will be what? 1 plus 0, that means 1. Okay. So let's see one more interesting question, and this question says when concentration of B alone was changed T half-life does not change. When concentration of A was doubled, rate doubled. The concentration of A doubled, rate also doubled. They are asking you rate law. Now see, let's take one by one. When concentration of B alone was changed, T half does not change. Concentration of B is changing, but half-life is not changing. Which order of reaction you are looking for? Half-life is constant. Half-life is constant in first order reaction. So for B, with respect to B, T half is constant. Now when I say T half is constant, that means it is of first order. So with respect to B, it is first order reaction. Now they say when the concentration of A was doubled, rate also doubled. That means the rate is proportional to, directly proportional to A. So for A, I can say that rate is directly proportional to A to the power of 1. So here we can say that this is also a first order reaction. So with respect to B, first order, with respect to A, first order. Okay. So I can write down rate law now. K, A to the power of 1, B to the power of 1. So this is the final rate law. Now what will be the order of reaction? Overall order 1 plus 1, 2. So overall order is 2. Okay. A simple question, I believe now. So let's come to the next question. It says we have a reaction A giving you B, and they have given some data. They have given you rate constant as 0.1, initial concentration as 1 molar. They are saying find the rate after 23 minutes. Now see, to find the rate after 23 minutes, I need to have a rate law, and to have a rate law, I need to have the order of reaction. Say R will be equals to K, A to the power of M. I know K, but I do not know order. Okay, so if I look at the units of K, I told you that please keep on having a watch on the unit of K. Unit of K is what? Per unit time, or per minute, per second. This is for first order reaction. Remember that. So our half of the problem is already solved. This is the first order reaction. So rate law will be R equals to K A. Now my job is to find out amount of A or the concentration of A after 23 minutes. We can do that very well. How? For first order reaction, I know that K is equals to 2.303 upon T log of initial amount A naught upon A, remaining amount after 23 minutes. So K is given as 0.1, 2.303, time taken is 23 minutes, log of A naught, A naught is 1 molar upon the remaining amount after 23 minutes. So this will be almost 10 into 0.1 will be 1. So 1 equals to log of 1 by A can be written as A inverse. So rearrange that will be log of A, and this minus will go there. I mean, this is minus of log A equals to 1, or you can say log of A will be how much? Minus 1, or you can say A will be, take the anti-log now, that will be 10 to power of minus 1 molar. 10 to power of minus 1 molar. Now using this rate law, rate will be K into amount of A remaining after 23 minutes. So K is how much? 0.1. How much is the amount of A? It is 10 to power of minus 1. So overall it will be 10 to power of minus 2 moles per liter per minute. Okay, so that will be our final answer. Okay.